Hi everyone, Mr. Neighbor here, and we're finishing up conservation of energy. This is a very interesting problem because it can be solved in two ways. One way with energy and one way with kinematics. So let's look at the energy way since we've been focusing on that first. So energy is always going to be conserved. The mechanical energy before will equal the mechanical energy afterwards. So here we have a certain time interval in which a 15 kilogram object free falls for 12 meters. How fast is it falling right before hitting the ground? It doesn't say this in the problem, but we're going to assume that at this 12 meters, when it was dropped, the ball was not moving, the object was at rest. So the potential energy before plus the kinetic energy before is equal to the potential energy after plus the kinetic energy after. So if it's not moving at the beginning, that means I can get rid of kinetic energy initially. And right before hitting the ground, it's not going to be at all above the ground. That means final potential energy doesn't exist. So I'm really looking at the potential energy at the start is going to equal the kinetic energy at the end. So let's write out these equations a little bit more specifically. We have mgh equals 1/2 mv squared. I notice both of these have a mass in it, so I could put all the numbers in and then do a lot of calculations with bigger numbers, or I could just realize I could divide the m over and then I don't have to worry about it. So now what I'm dealing with is 10 meters per second squared times 12 meters. A lot easier than multiplying that also by 15. And I'm taking that, I have 1/2, and I'm looking for the final velocity squared. So this is 120, 1/2 v squared. I will multiply by 2 then to get out 240. And then I have to square root to get v by itself, which will give me out approximately 15.5 meters per second. And remember, that's downward. Okay, so this is with energy. The blue was the energy way. Now let's do it with kinematics. We have a lot of different kinematics equations. We have the final velocity is equal to the initial velocity plus at. Our final position is equal to our initial position plus the velocity times time plus the 1/2 the acceleration times time squared. We have the final velocity squared is equal to the initial velocity squared plus 2 AD. We have all these, and a combination of them, or maybe one of them, can solve this problem. So let's kind of look at what we have. We have mass. Does any of these equations have mass in it? Nope. So must use something else. 12 meters, that's a displacement. Do I have that in any of these? It looks like this is the only equation that has that. And really, I don't have anything else, so I have to pretty much go with that. So let's look and see what we have. Final velocity. Do we know what that's going to be? Nope, that's what we're trying to find. Essentially, we know it's going to be 15.5. So I'm going to leave that there. Do I know what my initial velocity is? Yeah, I assumed it was going to be 0. So I'm not even going to write, well, I guess I can write it down. And I'll put a square around it because technically it's supposed to be squared, but it won't do anything because it's 0. Plus 2 times, what's our acceleration in this problem? It's gravity, so that's 10. Really, I should be putting a negative sign right there. And this should be a negative all the way through. But let's not worry about that right now. And then times time. Sorry, not time. Displacement here, which is 12 meters. I was looking at the wrong equations for a second. Okay, so 2 times 10 is 20. 20 times 12 is 240. Oh, I remember 240 coming up somewhere else. And it looks like it's the exact same as this part right here. So when I go ahead and do that and square root it, the final velocity is going to be 15.5 again. So the thing that's nice is you can choose which way you like to think about things. Some people love to think about energy because they think it's a lot simpler. You have two equations, essentially. You have mgh and 1/2 mv squared, and you're going to use them both every time. They might just get eliminated, though, at some point. So some people like that better. Some people just like constantly thinking about the kinematic equations because they really, really understand where these come from. This process of work and all that other stuff they're not so comfortable with. So use whatever you want. Sometimes there's only a certain amount of information given and you have to use energy, or vice versa, you have to use kinematics. This is a problem though where you can use both and choose. So use that knowledge to help you from now on.